Ladies and gentlemen, welcome. Today, in our online industry tutorial, we continue discussions on breakthroughs in scalable photonic circuits and wafer-scale integration. I'm John Pugh, Director of PIC and Quantum Technologies at Optica, and I'm very pleased today to welcome LIGENTEC, a Swiss-based company specializing in manufacturing photonic integrated circuits, or PICs, for high-tech sectors such as ground and space communication, quantum technologies, LiDAR, and biosensors. In today's tutorial, we'll hear from Michael Geiselmann, co-founder, president, and chief commercial officer of LIGENTEC, on how combining diverse materials and active components is pushing the boundaries of design flexibility and performance. Remember that this is a very interactive event. We have nearly 700 people registered, so please do ask your questions in the Q&A Zoom facility at the bottom of your screen, and we'll address them at the end of Michael's presentation. So Michael, the floor and the attention of everyone is yours to tell us about the exciting advancements from tutorial sponsors LIGENTEC.
Thank you very much, John. Yes, today I will talk about how to put active components to a very low loss passive photonic integration platform. And I assume that most of you know about photonic integration, but just probably there's a very few that are new to that. So why are we doing that? The electronic integration story was to put a lot of discrete components in a chip that is fabricatable with semiconductor fabrication techniques, and that took many research dollars from the beginning until today. But in especially this year and the last few months, we have seen the big success with AI on electronic integration, and also AI is driving photonics, and here it's similar. So we want to put the discrete components in from photonics that are on the left-hand side in a laboratory. We want to put that on a photonic integrated circuit and repeat the success of the electronic chip revolution. Our mission is to unleash the potential of photonic integrated circuits, or in short, let's pick it. And here you see two images, which already images the markets that we are addressing. On the left-hand side is a satellite to Earth communication or satellite to satellite communication, where we see that photonic integrated circuits make a big difference in terms of swap, to have a very compact device, and that can be put into space. But the quantities are probably not immense. And then on the right-hand side, a consumer product where quantities are very large and where you benefit a lot from the semiconductor fabrication techniques. LIGENTEC is a European PIC company with a global reach. We're the headquarters is in the center of Europe, in Switzerland, close to Lake Geneva. We're based in Lausanne, but we also have a daughter company in Corbeil in France that is just south of Paris, and another daughter company in Belgium, in Ghent, just an hour ride from Brussels. We have a bit more than 80 photonic enthusiasts that work hard to get the chips shipped all around the world. We have best-in-class photonic integrated circuits with very low loss. We can reach 0.2 dB per meter, and have different technologies to address different markets and different wavelength regions with an extensive PDK. And also since a couple of years, we are ISO 9001 certified to push further to industrialization of these photonic integrated circuits. To unleash the potential of PICs, so we have a seamless journey from idea to volume. We have customers that come to us with a GDS ready design that we then manufacture and test and ship to them. But we also have customers that come to us with an idea that they figured out they need the fabrication services that we have, but they don't necessarily know how to put their idea onto a chip layout. And here we support the customer with design and layout, and then do the chip manufacturing for them, and even with partners also provide them a packaged chip. In the end, the customer takes that and puts that in a module and product, and the IP from the customer is in the product IP and the schematics of the module, the system IP, whereas our IP is in the manufacturing and the technology development of that manufacturing. So the commercial offerings that we have is we have early entry R&D and prototyping. We have multi-project wafer runs that run in an open access. So you sign a design kit license agreement, and you get access to the PDK. And then you can participate in, for example, a multi-project wafer run where you share the design space of a reticle, and also the cost of a wafer run with other customers, but you then only get the chips that you designed. We also have development projects with selected customers where we have high flexibility and PIC and optic competence to get the customer development into a product. And in the end, the why we are here is to supply our customers with photonic integrated circuits with quality and guarantee. And here we have picked a wonderful partner in Europe, which is X-FAB. The fab is also located in south of Paris in Corbeil. And so we really see the great benefits to have X-FAB as a partner, because we run in the fab all standard silicon nitride stacks. So even the low volume multi-project wafer run, as it's a standard stack, is run at the 200 millimeter CMOS production line. So we can run pilot and niche quantities up to high volume. So you don't need to change a fab if you start low and then build your volume up to a very high volume production. It can all stay in the same fab, so you don't need to transfer your process. And the advantage of being with a automotive qualified CMOS fab is that there is a highly automated process flow, and there is equipment that are ready to use for CMOS processes, and that we can piggyback on, and where we installed our proprietary silicon nitride process. So as I mentioned, X-FAB is automotive qualified and medical ISO compliant, and that also benefits to our customers, that we can offer a very good service and quality and reliability to our customers. Our customers are in three segments. We have customers in computing that include customers in quantum computing, neuromorphic computing, and optical I/O. And then the second segment is connectivity, which is customers from telecom and datacom, optical circuit switching, reaching to satellite communication or QKD, so everything that connects to ports where you need to transfer information. And then sensing, where we have probably the broadest spread in customers, that reaches from optical coherence tomography to customers doing LiDAR, where you want to sense the distance in automated driving, or in robots, or even in industrial plants. And then atomic clocks and GPS-less navigation, to biosensing, where customers want to sense an analyte that is shown in that picture through photonic integrated circuits, or with photonic integrated circuits, and then up to fiber sensing and metrology. And here again, it's the two worlds. One is, some of these applications are probably niche, but other applications have very high volume. And we serve these application with our standard platform, where we have three different thicknesses. The AN stands for all nitride, so we have three different nitride base thicknesses, and then one base thickness then has then also other, or one base platform then also has other components, such as second or third nitride layers, heater modules, RIP module for the base waveguide, and local cladding opening, where you then can access the evanescent field of the waveguide, which is very important for customers that do sensing, or for us to integrate other materials, which is the topic of the talk today, to get evanescent coupling between the base platform and additional active materials to integrate them heterogeneously. And why do we have different thicknesses? This is mainly to cover wavelength operation from 400 nanometer to 4 micron. So silicon nitride has the advantage that you have a very broad transmission spectra in silicon nitride, but the waveguide needs to be adapted if you have a very short or very long wavelength region. And one of our core competences is to have a very confined mode in the waveguide, so we can combine very low losses with a very good confinement. And that platform goes with extensive PDK. And what is included in such a PDK, a process design kit? We have different building blocks that are included in the PDK, reaching from spirals to Mach-Zehnder interferometers with MMIs, directional couplers, to heater elements or ring resonators that you can tune with heaters. This PDK is supported by several EDA providers and software houses, where we work in close partnership with them to provide the best customer experience when they want to design, layout, and simulate the circuit of a photonic integrated circuit. It goes without saying that the software is only one part and simulation is only one part. You also need to test the PDK components. So all the building blocks that I just mentioned, they're tested within a wafer, from wafer to wafer, and from batch to batch, and like that we build statistics of the process, but also of the different building blocks. So if you put one building block in your circuit, we have extensive measurement data and statistics that you can be assured that this building blocks works like predicted in the design manual. And this is one example for it. So we have here a MMI which was designed to have a 50-50 splitting ratio. And if you look at the splitting ratio that is shown here on the color scale, we are tracking a splitting ratio from 49.79 to 50.14. And this is kind of the outliers, and have a very good performance across the whole wafer of almost perfect 50-50 .0 splitting ratio. In addition to building blocks, we obviously also track process performance, and one key requirement of process performance is low loss propagation. We have the best silicon nitride propagation loss for photonic integrated circuits, and here we have 200 millimeter wafer maps where we measure the propagation loss within a wafer, and also wafer to wafer. So you see the different wafer plots here on the lower left, where we do box plots of within wafer and wafer to wafer cutback based propagation loss. So you have kind of different spirals from different lengths, and then retrieve from that measurement the propagation loss in such a waveguide structure. And here we have to distinguish of the geometry of the waveguide structure, which is very important if we talk about propagation losses. We have a 1 micron by 350 nanometer waveguides where we get around 4 dB per meter propagation loss. And if we make the waveguide wider in a straight section, then we can get even below actually it's 0.2 dB per meter propagation loss that we can get in a wide waveguide at 1550 nanometer wavelength. And when you have such a very low loss propagation platform, actually it's amazing what you can do with it. You can put a 7 meter of a spiral delay line on a 16 by 8 square millimeter chip. So that's a chip that is smaller than your fingertip, and you have a 7 meter delay in nitride waveguide with a fiber to fiber loss that can reach below 8 dB, including coupling of the fiber to the chip and the propagation loss in the circuit. And that is only possible because we combine very low loss with a relatively high confinement of the wave of the mode. and can, like this, get a very compact chip size with very low losses. And as I mentioned, it also is very important to get a very good spot size converter to have minimal losses of fiber to chip. And here we see a chip with fiber arrays on the left and right, and the mode field diameter image of the mode, how it comes out of the chip, and the packaged fiber to fiber loss of these spot size converters with fiber arrays are below 1 dB per facet, so 2 dB from fiber to fiber loss. And these, so we have had many different spot size converter requirements for different customers, because sometimes it's in C band and O band, and also adjusting to special SOA or laser spot size converters. So we have gained a lot of experience in modeling those, and here we show that the spot size converter itself is very resistant to excess loss for displacement. So we show here in that graph, the red line is a horizontal displacement, and the vertical and the blue line, and we get excess loss for a displacement of 300 nanometer below 0.03 dB. And to make that useful to also customers that don't have good test setups, we also offer a PDK for packaging, where the connectors are the connections on the chip are already predefined for fiber in and fiber out, and heater pads where to connect them, to have a simple and cost-effective demonstrator through our partner network to get the chip verification without the need of an optical bench. And last but not least, for this very low loss passive platform, we also integrated heaters, very reliable and very high performant heaters, where you can achieve in a ring resonator or a Mach-Zehner interferometer several pi phase shifts. And in combination with an undercut, you get a pi phase shift of below 5 milliwatt, what was demonstrated in a customer circuit. So this is the very well performing passive platform, and now we know that we need also other active components for certain applications. And our approach is to use the silicon nitride as a base platform for the general circuitry, with our comprehensive PDK and design manual, the best platform for passive components, and very good optical I/O, and a scalable platform that can be fabricated in volume, and combine that with heterogeneous integration for actives. And here heterogeneous integration is the broad name for integrating active components into the base platform. And that reaches from detection to modulation to amplification and laser. And each of these might be integrated with different techniques, and I will talk you through some of these different techniques in the next few slides. So again, we start from a 200 millimeter wafer that is fabricated in a 200 millimeter CMOS line, and then we integrate for very low loss RF modulation. We integrate that with lithium niobate. And here that is a final chip, where on the left hand side you see are the passive components which are made of nitride. So you see splitters and the waveguides in nitride in the blue region. And then you go to the active region, which is the lithium niobate, which is shown here in green, and the yellow part, this is the electrodes where we modulate these push-pull Machzehnder interferometers with lithium niobate. And then we go down again into the nitride and back to the passive components with extremely good edge coupling of the chip. So we combine the best passive platform with that we have demonstrated we can fabricate to volume, which has nitride and heater integration, and put the thin film lithium niobate for modulation only where needed. So this only takes the essential components for lithium niobate. All other components remain in silicon nitride, and all standard building blocks are available from years of experience of shaping the PDK, plus testing and getting all the statistics of the PDK in silicon nitride. And so the lithium niobate here is only the addition for modulation, for electro-optical modulation, but all the other building blocks have been tested extensively and since many years, and are readily available in the PDK. And that hybrid mode approach actually does not lower the propagation loss. So the propagation loss we have demonstrated with the silicon nitride is not altered significantly. So we still get propagation losses down to the level of a few dB per meter in this hybrid mode. In addition, probably just to explain, so this hybrid mode is guided by a silicon nitride waveguide, and on top you have a thin film lithium niobate film that is not structured, but as the lithium niobate has a higher refractive index than oxide and silicon nitride, the mode is pushed into the thin film lithium niobate, and as I mentioned, the propagation loss is not altered, and the escalator loss. So to go from a nitride only waveguide to that hybrid mode, we can get that escalator loss down to 10 millidB. So in the end, you can have a fiber to fiber end-to-end loss below 1.5 dB. So this is again a schematic how we operate. So we have the edge couplers in and 2x2 couplers in nitride, and then we transfer the mode into this hybrid mode, which is here called a transition mode from this paper from UC San Diego and then you get in your hybrid mode where the nitride is guiding, but the mode is mainly pushed in the thin film lithium niobate, where you then have your modulation with the electrodes in the thin film lithium niobate. And then you do the same thing again. You go to the transition mode and then back to the feeder mode to the silicon nitride. And with that, we can have a combination of a very low loss platform with very high speed modulation, which was shown in a research collaboration that we have with University of San Diego, and published a preprint archive this year on electro optical modulation on that hybrid platform, nitrides to lithium niobate, with a bandwidth up to 110 gigahertz that was measured by our collaborators in San Diego. But modulation is not the only thing that is needed in a photonic integrated circuit. You also need for many applications detection, and here we took a different integration approach to get PDs integrated also on a wafer scale level. And so here you see again a 200 millimeter wafer with integrated PDs. So the photodetectors are sitting here on the right hand side of that photonic integrated circuit, and this is here you actually can see nicely this local cladding opening, and then that tiny golden dot, that's the photodetector and the contacts. And we chose to use microtransfer printing here for integrating PDs, where we source 3,5 PDs from a source substrate, where they have prefabricated photodetectors on that substrate. And then we go to our silicon nitride target wafer and use this technique called microtransfer printing, where you take like a stamp, you take that photodetector, pick it up, and then pick and place it to your target wafer, where you then can integrate this on a wafer level scale, these PDs on a silicon nitride. And this is the key specs that we are offering. Very low dark current with very high responsivity, and again very low insertion loss of the component. And the advantage is the same than before. You can use all the PDK components that are developed in the nitride process, which is shown here in the green. So the green waveguide is the nitride, and then with this local cladding opening, we integrate the photodetector onto the wafer, and through evanescent coupling of the waveguide to the photodetector, we detect the light on the PD. And here is an image on the coupon. So these the PDs that we pick and place, we call them coupons. And here these all these dots here are the PD coupons, and we see that the source dies have similar dark current before and after processing, which assures that this processing step is working for integrating 3,5 PDs on a low loss nitride circuit. And so the advantage is really we activate our platform with having very low loss components such as AWGs, and here you have you come in with a light in the AWG from the edge. You couple the light and split it in the AWG, and then with the PDs you can do your readout directly on the chip. Last but not least, the next challenge is lasers, and laser integration is probably the holy grail. At the moment, we have customers that use what we call a hybrid integration approach to get, for example, a tunable narrow line with laser. And so here they combine the properties of low loss silicon nitride on the left, shown on the left hand side here, with a gain chip or so either a reflective SOA or a gain chip, where you have in your nitride circuit, you get you do a layout of an external cavity laser, and then, for example, with a Vernier effect or other effects which can be found also on our website, we then can get to a laser integration that has two benefits. One benefit is that you get a narrowing of the line width of your laser chip. So from megahertz you can go down to single digit kilohertz or below. You have a very good power output, very good signal to noise, and you have a very large tuning range of your laser, which is given that we integrate again here heater phase shifters onto the low loss nitride platform to get access to tuning and of the laser wavelength. And as I mentioned initially, so this can be done in C-band, but that can also be done for different wavelength region, either on the shorter or the longer wavelength regions. And here is an example for doing the exact same physics. So you have a silicon nitride pick here on the right hand side, and you attach it to a laser at either 2 micron or 2.5 micron. You create your external cavity layout on the silicon nitride photonic integrated circuit with the heaters as tuning elements, and then you get an output here for one laser covering a wavelength range from 9037 to 2017 nanometers. And then if you change the SOA, if you change your laser material, you then go, you can get similar very good results for 2470 to 2640 nanometer tuning of the wavelength. So where do we go next? We have several projects that is still in a research phase to look at integration of lasers that is heterogeneous integration. And here we collaborate in a European project with the Photonics research group in Ghent to get the lasers on our nitride platform through microtransfer printing, and then have a milliwatt level output of these lasers through the evanescent coupling of the laser material with our waveguide that is opened of the cladding, and then allows evanescent coupling to the laser material. And we are also looking into gain, getting a gain on the chip. So there's different approaches how to get gain on the chip. There is either deposition of a doped material or directly implantation of rare earth ions into the waveguide to get a gain section monolithically integrated into a photonic integrated circuits. And here again, combining the very low loss with an active component. And here in this paper, collaborators have shown to get a 50 times pulse amplification when so you come in with your laser, and then have quite some centimeters of coverage where you again guide the mode in the nitride, but the mode sees the thulium doped aluminum oxide that is deposited on top, and like that you get a gain section over several centimeters, and at the output of the chip get a 50 times pulse amplification of your laser. So we don't do all of that alone. Here in Europe, we have we're developing a photonics industrial value chain under the umbrella of CHIPS JU, and we have a project where X-FAB and LIGENTEC are key providers of this photonic integrated circuits, but it comes also with a whole value chain. So you have to think from very beginning, from the photonic design and EDA to the packaging and system applications. And in this consortium, we provide photonic integrated circuits for different end customers, and construct photonic industrial value chain that is operating out of Europe. With that, I would like to thank you for your attention, and let's pick it. And also an advertisement that we are hiring in Switzerland and France. So check our website for open positions. And I'm happy to answer any questions that you might have.
Great. Michael Geiselmann, thank you so much. Incredible progress from LIGENTEC as always. So we do have some questions in the audience. So you showed the three nitride thicknesses you offer as standard. If a customer were to come and choose a custom thickness, what would be the minimum order quantity needed for that?
So we have the, like I presented here. So we have the possibility to have R&D. That's if a customer shows a significant um, impact of its application in the future, we are happy to engage in R&D and development projects, where we then together can scale such a customer. However, it is it we cannot do that with hundreds of customers. So we really try to find a way where probably we can have use some of the base processes and only adapt a few things to a customer. But in the end, we have done such projects with several customers and offer these custom thicknesses.
Thanks, Michael. And there's a couple of questions about using these picks in the visible range. You quoted the sort of loss numbers at 1550. What are the kind of loss numbers in the visible, for example?
So yeah, that very good question. These loss numbers that we get here for 1550. So loss is dependent on the nitride, so on the material itself, but then also on the line the lineage roughness that you see, and or that the mode is seeing. And here I already showed, like, if you make a waveguide wider, you lower the losses. So this is why it's important always to refer to what waveguide dimensions we're talking about. At the moment, if you go to a single mode waveguide at in the range of 5 to 700 um, nanometers in wavelength, you are probably an order of magnitude higher in losses, because you have the the scattering loss from the lineage roughness scales to the cube with the wavelength. So the lower the wavelength, the more exposed it is to the waveguide roughness.
And we had a couple of questions about integrating vertical emitters with picks. Is that something you offer a standard service for?
Yeah, so what there's several techniques, like vertical emitters. Is it for lasers or like VCSELs or
Yeah, I would say VCSELs. VCSELs is the question. Yeah.
yeah, so VCSELs, we again can do that cladding opening, and then have a grating coupler where we then take the vertically emitted light through a grating coupler into the waveguide.
And when you're integrating TFLN with the silicon nitride, is there any limitation on the patterning of the TFLN? We have a question from Michael, for example, on are you able to offer TFLN ring resonators?
So that we are able to offer TFLN ring resonators. The what we Where we are limited in is the bend radius. So we just have to to make sure that the bend is not too tight, that we can still guide the light with a nitride waveguide. And then we have, but this is in a general thing. Then in lithium niobate, you have a certain cut and a certain axis in the lithium niobate, and this has to be taken into account. But you can do bends in the circuit, and you can do ring resonators, but you're limited by how small these ring resonators can be made.
And one of the biggest cost drivers in PICs today is test and measurement. I think you showed it in the time sequence. And often that accounts for a large fraction of the total device cost. How is LIGENTEC approaching the challenge of reducing this test overhead, essentially?
Yeah, so we have inline testing, and we do qualification testing of the circuits before sending them out. So we provide the customer with circuits that are tested, so we can test in-house. But we I think the limitation is the what needs to be tested. If now someone comes and says, I want to test my quantum algorithm of the circuit, that takes more test equipment, that is more in test houses or on the customer side. But if it's customers with standard building blocks, and the standard circuitry, we can take a lot of that work already from at the fabrication site.
And there's a just returning to the Tiflin-based modulator. What is the V-Pi L of your modulator that you showed?
Yeah, so you have we have different modulators for different applications, targeting different speeds. And the one that I showed for the 110 gigahertz was probably around 3 volt centimeter, but we have a new tape out where we target 2 volt centimeter for VPL.
And there's a question on the challenges you have estimating wafer bow in the challenges. And when you start to actually pattern, what are the challenges there with estimating that? And once you've patterned the wafer, do you see the bow varying?
That's for the fabrication experts that I will not comment.
Okay. And a question I've heard a lot about recently is with the fiber couplers. I think coupling light into a chip remains one of the sort of biggest challenges with commercializing a PEC system. Are you working with some partners on achieving sort of low loss detachable connectors and things like that?
So what I cannot show everything here. We have we we believe that the more you do on the chip already, that that saves you a lot in packaging cost afterwards. So we have customers with whom we develop spot size converters that are way below this 1 dB per facet. And so we believe that the more you can do on the chip side, which is then integrated in your semiconductor process flow, the less packaging cost comes then afterwards.
And Michael, you highlighted towards the end of the presentation strong gallium antimonide hybrid laser performance with your silicon nitride platform into the 2 to 2.5 micron wavelength range. Do you see this band becoming more widely used in the future? And what application would we see for that?
Yeah, so there's what I see is that we have these different wavelengths. They're mainly targeting uh, the different thicknesses are targeting different wavelength regions, whereas the 150 nanometers mostly targeting visible applications, and then O-band, C-band, 350, and C-band up with 800 nanometer thickness. And there is more coming in the 2 micron range, but this is still compared to other wavelength regions a lower demand, but still with probably higher impact, because you do gas sensing or defense applications that are in these wavelength regions, which is then probably a higher strategical impact for the customer.
And what is the estimated timeline? Is it something you're offering now, this laser integration on the silicon nitride platform with MPW runs, or is that something you'll be offering
Yeah,
in the near?
so we have many customers that do this approach, and we have built up the supply chain that we can offer that through the supply chain. We don't offer that as a standard building block in a MPW, but with an MPW chip that we can discuss with the customer the needs and integrate that in the supply chain, so the customer gets a laser in the end delivered.
Michael, you work with so many people. I'm just wondering, are there any partnerships or ecosystem moves, be it foundry, assembly, module integrators, that you're actively seeking at LIGENTEC that may be in the audience?
I believe from all that I have shown, we are working, as you mentioned, with many partners, but we are always happy to speak to material providers, to packaging providers. That is sometimes also driven from our customers, to have in different geography regions, different providers. So happy to discuss with material providers or on the packaging side, in the integration of the materials.
And what is the best way to contact you or LIGENTEC?
The best way is to send an email to either through our web form, or to info@ligentech.com, and there you will be served very quickly.
Fantastic. So, Michael, we start on time, we finish on time. So please do get in touch with the team at LIGENTEC and or Michael, or through me, I can introduce you to the team, particularly if you're looking to partner and use their foundry services. So once again, I thank Michael and all of LIGENTEC for sponsoring this industry tutorial brought to you by the great team around me at Optica. So thank you so much for attending, for your attention and for your questions. And bye for now. Thank you.
Thank you.